In this video, we continue to look at the exponent rules inside of groups with a multiplicative operation. I want to remind you that the author of our textbook has stated the exponent rules in Theorem 3.23. You should have already copied this down in your notes. In the previous video, we proved property 1. In this video, we will be working on the proof of property 2. 2 videos ago, we proved this useful lemma about negative exponents, that g to the k to the negative 1 is g to the minus 1 raised to the k, and they both can be then written as g to the minus k. So without any further ado, let's start working on the proof of the second part of Theorem 3.23. In other words, we want to prove that g to the m raised to the n is equal to g to the mn in a group. And this is for all m's and n's pulled from the set of integers. Just like the proof of part 1 of this theorem, this proof is going to break down into 4 cases. And case 1 is the easy case. M and n are both bigger than 0. And in this case, the expression g to the m raised to the n can be understood in terms of the meaning of powers where the power is a natural number. We have g to the m times g to the m all the way up to g to the m, and we are looking at n copies of g to the m. But each one of those g to the m's itself can be replaced by n copies of g. And so what we're looking at is m copies of g in each one of these little parentheses. And we have a grand total of n copies of m copies of g. And that means what we've got is we have a total of m times n copies of g on that list. And so we wind up saying that this is indeed g to the m times n. So case 1 is done. Case 2 is going to be when m is bigger than or equal to 0 and n is less than or equal to 0. And in this particular case, what I want to do in order to be able to track those minus signs down, I am going to let that negative n, rather I'm going to let that n that is less than or equal to 0 be written as minus 1 times k, where k is a positive integer. And this will let me understand what the exponents mean very naturally. So under this particular set of circumstances, g to the m raised to the n is going to be g raised to the minus k. But I know from our lemma that I can rewrite this as, that should be g to the m raised to the minus k. And I know from our lemma that I can write this as g to the m's inverse raised to the k. But I also know what to deal with this inside stuff here. Our lemma applies to this mess here as well, and when we apply that, we get this is equal to g to the negative 1 to the m, and then we're going to be raising that to the k. So this is our lemma kicking in. So at this point we have g to the m raised to the n is equal to g to the negative 1 raised to the positive integer m raised to the positive integer k. And that's just going to be g to the negative 1 to the mk by the previous part of this particular proof. Because m and k are both positive integers. Well, at this point, I can now rewrite this using our lemma as g to the minus mk, but g to the minus mk is g, let me clean up my notation just a bit there. G to the minus mk is g to the mn since minus mk is equal to mn, because if you remember, minus k and n are the same thing. So case 2 is done. Well, let's now look at case 3. Case 3. Case 3, we're going to let n be less than or equal to 0 and n be bigger than or equal to 0. And as before, I want to be able to sort out those minus signs very carefully, so I am going to let m be equal to minus L, or minus 1 times L, where L is a positive integer. So what's going on in this case? G to the m raised to the n is now going to be g to the minus L raised to the n. But I know how to deal with g to the minus L. G to the minus L is just g to the L raised to the negative 1, and then I'm going to raise that to the n. And this is my lemma kicking in. But I know how to deal with the inverse raised to the n. That's going to be g to the L raised to the n's inverse. And that is also by our lemma. But now the previous part of the problem kicks in because both L and M are positive numbers. This is g to the L n. I made a copying mistake there. Raised to the negative 1. And this is by the previous part of our theorem. So, by previous part of this proof. And once I have that, I can then use our lemma to say that this is g to the minus ln. So that's by our lemma. And minus ln is the same thing as g to the mn, since minus ln is equal to mn because we set at the start m being equal to minus L. And consequently, case 3 is done. So let's now move on to case 4. In case 4, m is going to be less than or equal to 0, and n is going to be less than or equal to 0. So for convenience sake, we are going to write, and let me put this in as separate color, because it helps to highlight this. We're going to write m is equal to minus L, and we're going to set n is equal to minus k, where L and k are non-negative integers. And so we know everything that we might want to know about g to the L and g to the k. So now look at this. G to the m raised to the n is going to be, and here I'm going to put the new stuff in a different color. That g to the m is going to be g to the minus L, and then we're going to raise that to the n. And I'm going to deal with the outside exponent after I deal with this first exponent. By our lemma, g to the minus l is nothing more than g to the l's multiplicative inverse. And then I want to raise that to the n. Now, what I want to do at this stage is break down that n into a minus k. So this is going to be g to the l's multiplicative inverse is going to be raised to the minus k. Now, what I want to do at this point is break that minus k apart. And I'm going to basically be thinking about, I want a new symbol for this mess. I'm going to let b equal g to the l's inverse. So what I'm looking at this point is b being raised to the minus k. And I know how to do that. That's going to be nothing more than b's inverse raised to the k, because k is a positive integer. This is by our lemma. Now what I'm going to do is I'm going to be thinking about what is b inverse. And we have that b is equal to this complicated mess. So I'm actually going to let a be g to the l, and then b is a inverse. And at that point, I can see that b inverse is a inverse's inverse. In other words, it's just equal to a. And so what I can say then is that this expression here simplifies to a being raised to the k. Well, a is nothing more than g to the l. So this then becomes g to the l raised to the k, and l and k are both positive, so by the first part of this proof, that is l and k. So by first part of proof. But now what I want to remember is the final little piece of the puzzle. So I want to recall that if we go all the way back to the top, we know that m is equal to minus l and n is equal to minus k. And consequently, and let's write that down, m equals minus l and n equals minus k. So lk and mn are exactly the same number because mn is nothing more than minus l times minus k, and that's a minus times a minus, so we get lk. So what we now have then is that g to the m times n is equal to g to the lk, but g to the lk is g to the mn, and that completes the proof of the second part of this theorem.